Bismillahirrahmanirrahim. Good morning, everybody. This is the last lecture in our course, and in this lecture, we are going to consider the second type of integration, which is definite integration. We are going to start by describing the mathematical definition of definite integration, and this is very important because based on this definition, definite integration are used in many application. And also we are going to mention the what's called fundamental theorem of calculus, which presents the simplest way to evaluate such type of integration by linking this integration with the first type of integration, which is the indefinite integration. And then we are going to consider different example to evaluate definite integration and relate it to some important cases. Let's start with the definition. Simply speaking, the definite integration is the limit of a sum. You can remember that when we describe the definition of differentiation is a limit of a ratio that gives finally the instantaneous rate of change. Now we are going to consider the mathematical definition of definite integration, which is simply speaking limit of a sum. Why you are interested in the limit of sum? Actually, because it exists in many problems. Many problems are solved, or their solution are given in terms of a limit of a sum. It is a summation, but you have to consider the limiting case of this summation. Let's start with this well-known problem, which is the area problem. We want to find the area under the curve of this function, for example, from x equal 1 up to x equal 5. This area doesn't have a geometrical rule to evaluate. So how to evaluate this area? The first idea is to make some sort of approximation. Let's divide this interval from 1 up to 5 into 4 sub-intervals, and for each sub-interval we approximate the area below this curve in this sub-interval with this simple rectangle. The area of this rectangle can be calculated easily, and also for this rectangle, and this rectangle. If you sum now the areas of these 4 rectangles, you get the area. Actually, you get an approximate value of the area because you have an error. Some area are not included in your calculation. How to improve this approximation? You can increase the number of sub-rectangle. Instead of dividing this interval from up to 5 into 4 sub-intervals, you can divide it into 10 sub-interval, into 100 sub-interval, into 1000 sub-interval. And as you increase the number of sub-intervals, the approximation is better and better. But what about the exact value? The exact value is reaches when n equals infinity, or you can say that the actual value, the actual area, is the limit of this summation, the summation of such areas, as the number of sub-intervals, the sum number of rectangles, approaches infinity. When the step size you take to divide this interval into n sub-interval, this step size approaches 0. So the actual area, the exact area, is defined as a limit of a sum, So we define in general the definite integral of some function f of x from x equal a up to x equal b as the limit of this sum, and this sum is called Riemann sum. What is the content of this sum? This sum represents the area. The area of any of these rectangle is the length times width. The length is the value of the function at this point, and then at this point, and then at this point, to give the different heights of such rectangles. What about the width? The width is the step size, which is usually called delta x. So each term in the summation is given by this product, length times width. And then you sum such areas. Such summation is usually called Riemann sum. Summation of this form, the function evaluated at different points in the interval, and then multiplied by the step size. And then you make a sum. This is usually called Riemann sum. So the area is defined as the limit of this Riemann sum. And so we define this as the definite integral. We say that the definite integral of the function f of x from a up to b is defined mathematically by the limit of this summation. And from a practical point of or application point of view, this limit of the sum represents the area under the curve from x equal a up to x equal b. But the important question now is, does this definite integral apply only for computing area? No, because actually such summation and the limit of this summation exist in many applications. The same summation and the same solution that based on taking the limit of this summation. Consider, for example, we have a function f of x, but now we are not interested basically in computing the area under this graph, but actually this function represents the velocity function as a function of time. It is a variable velocity function. The velocity as this time is this value. The velocity at this time is this value, and so on. So we have variable velocity function. The question now is that what about the travel distance? We want to compute based on this variable velocity function the travel distance. If this velocity function is a constant function, you are moving with a constant velocity, then simply speaking the travel distance is the value of this velocity constant multiplied by the time interval, the time period. But now what about the variable velocity function? In this case you have to divide the total interval, the total time interval, into sub-time intervals. Over this time interval you can consider the velocity to be constant velocity, some sort of approximation. In this case, if you accept that the velocity over this small interval is a constant velocity, then the travel distance during this small subinterval is given by this constant velocity, this height, multiplied by this time period, this width. So actually it is again this summation, the value of the function multiplied by delta x. The value in this case represents the constant velocity multiplied by the small time period over which this velocity is constant. And then you add the travel distance over this interval to the travel distance over this interval to the travel distance over this interval, and finally you get an approximate value of the travel distance. What about the exact travel distance? You have to take the limit. You have to increase the number of subintervals. You have to make this time period very small. If you want the exact, you have to consider as this time period approaches 0. So actually the travel distance, not now the area, the travel distance is the limit of this Riemann sum. Not only this problem, many problems. Consider, for example, this function represent a force function. Somebody is moving and the acting force is a variable force function. It is a function of the position of this object. If this force is a constant, then you can compute the work done to move the object from this position to this position by simply speaking multiplying this constant velocity by the distance, f times d. But what about the case of variable force function? In this case you have to apply similar idea. You can assume that over this distance the force is constant, and so the work done to move the object from this position to this position is this constant force multiplied by this small distance. What about the work done over this small distance? Again, the constant force multiplied by this distance, and work done over this distance is the constant force, assuming it is constant now, multiplied by this travel distance, and so on. So you have again such summation to compute the work done over each of these subdistance, and then you make summation. And if you want the exact work done, you have to take the limit as the number of subintervals approaches infinity. So such limit of this Riemann sum exists in many applications. So it is very important to how to calculate such limit of a summation. So we name it definite integral for this function from a up to b. It is a definite integral. It is integration because you add this to this to this to this to compute your final target. So the name integration, and it is definite because you are interested in specific interval from a up to b. So this is the definition of definite integral, and based on this definition, definite integral exists in many applications. Now the important question, how to evaluate this definite integration. Basically, you have to evaluate it by computing this limit. You formulate this summation as a function of n, and then take the limit of this summation as n tends to infinity, or equivalently delta x approaches 0. You have to solve this limiting problem. But now we have a very simple approach to solve this problem and evaluate this definite integral based on what's called fundamental theorem of calculus. Fundamental theorem of calculus says that to evaluate this definite integral from a up to b, you have only to do two things. The first thing is to find the antiderivative of f of x. You have to solve the problem of indefinite integration of this function, finding f capital. This is the first step. The second step is a very simple step. You make only substitution. You substitute with b, substitute with a in this antiderivative, and then take the difference. This is the simplest way to evaluate this definite integration. But here it is based on solving the problem of indefinite integration. You have first to find the antiderivative of this f of x based on, for example, what we have described in the previous two lectures. And actually we're going to consider the proof of this fundamental theorem as a mathematical proof. But actually, if you consider this function f of x to be, for example, a velocity function, this result is very obvious. Because if f small is a velocity function, then this integration, as we described, represents the total travel distance from t equal a up to t equal b. So this integration represents the total travel distance based on assuming that f is a velocity function. From another perspective, if you integrate f as an indefinite integration, you get f capital. In this case, f capital represents the displacement function. F is the velocity function, f small, so f capital is the velocity function. Now, if you substitute in this displacement function with the end time point and the initial time point, and take the difference, what is the value of this difference? Actually, this value represents the total travel distance, the displacement. So both sides represent actually the total travel distance or the displacement. So this result is very obvious if you consider f to be the velocity function. Both represent the total displacement of this object. But actually this result is valid in general, not only for this example based on a velocity function. And now we are going to consider the mathematical proof of this theorem. To prove this theorem, we start with this side and say that this side can in general be viewed as the area under the graph of x from x equal a up to x equal b. So the value of this integration represents the area under this graph from a up to b. Now let's define the area from a to a general point x as a function a of x. A of x represents the area from the point a to general point, a variable point x. And finally, we are going to consider x to be b. But now, consider a of x to be the area starting from this fixed point a to any variable point x. Now, if you increase x with a small interval, increase with a small step h, you arrive at the point x plus h. Now, what about a of x plus h? It is the area from a up to x plus h. And you can say that it is the same area, a of x, but you have to add this red area. This red area has a very small width, so you can consider it as a rectangle whose height is f of x and width equal h. So the area from a up to x plus h is a of x plus the area of this small rectangle with width f of x and height with height f of x and width h. So a of x plus h equals approximately a of x plus h times f of x. Now, if you separate f of x in aside, then you have this formula: f of x equal approximately a of x plus h minus a of x over h. This ratio is very similar to the ratio exists in the definition of differentiation, the derivative definition. So now we're going to consider the limit of both sides as h approaches infinity. In this case, this side as h approaches infinity is actually the derivative of this function with respect to x. It is the derivative of the function a with respect to x. And in this side, f of x is not a function of h. It is not changing with h. So this side is again f of x. So now we arrive at this result: f of x equal dA by dx. If you make an indefinite integration of both sides, then the antiderivative of this, the indefinite integration, is f capital of x, and then the integration of this derivative gives the original function a, and then you add the integration constant. In order to evaluate this integration constant, you can put x equal 0. X equal a. In this side you have f of a. In this side you have a of a. Recall that a of x is the area from a to any x. If you put x equal a, now it is the area from a up to a. Clearly it is 0. From a to the same point, the area equal 0. So when you put x equal a, this term will be 0. And this term will be f of a, so c equal f of a. So the result is that a of x equal f of x minus f of a. Now if you put x equal b, you get what we want to prove: a of b equal f of b minus f of a. And a of b is the total area from a up to b, which gives the definite integral from a up to b as f of b minus f of a. So this is what's called fundamental theorem of calculus, and it gives the simplest way to evaluate this definite integration, but recall that it is based on you can find the antiderivative of this function. You can find f capital starting from f small. You have first to make an indefinite integration and then make substitution. Now we can also consider the fundamental theorem of calculus to represent what's called net change theorem. Net change theorem can be described if you consider this function, or this result, fundamental theorem of calculus again. Now, if you consider, as we said, f to be, for example, the velocity function, then f capital is a displacement function, and this difference represents the change in this displacement function. The change in this displacement function. This is the initial position and this is the final position. So the difference gives the net change in this displacement function. And this side represents this net change as an integration. But now it is an integration of the derivative of this function. This is the general result. This is a general result based on this theorem. The net change in some function is given by the definite integration of the rate of change of this function. Again, net change in some function, f capital, fb minus fa. This is the initial value of the function, and this is the final value of the function. So this difference represents the net change in the function is given by the definite integration of the rate of a change in this function, f, because f is the derivative of f capital. Again, if you consider the f capital to be the displacement function, so now its derivative is the velocity function. So now if you integrate this rate of change in the displacement function, which is the velocity function, you obtain the net change in the original function, which is the displacement function. This is the general result. Here you have some function f capital, and here you have f small, which is the derivative f dash or f prime of x. Let's consider example based on this consideration of the fundamental theorem of calculus to present the net change. Assume that water flow from the bottom of some tank based on or described by this rate. This is the rate of change, the rate of by which this fluid flow from the bottom of the tank. So this rate represent actually the derivative of the volume function, because the volume function represents the quantity of water in this tank at any time t. And if you take the derivative, volume is changing now because the water flow from the bottom of this tank. So now if you consider the derivative of this volume function, it is the rate of change in the volume in this tank. So it is the rate by which the water flow from this tank. So actually this rate is the derivative, It is the derivative of the volume function, how the quantity of water in this tank at any time t. So the question now is, we want to find the amount of water that flow from the tank during the first 10 minutes from t equals 0 up to t equal 10. So now you can say the amount of water, this is a net change in the water volume. It is a net change. It is the final volume after 10 minutes minus the initial volume. This is the amount that flow from the tank during this period. How to find it? How to find this net change? By a definite integration. Definite integration over this period of which function? Of the rate function. To find the net change in this volume function, you have to integrate the rate of change in this volume function. So we integrate the rate function over this time interval. How to find this integration? Simply by applying fundamental theorem of calculus. We find first the indefinite integration of this function. The integration of this will be 200t. The integration of this will be t squared over 2. So it is 2t squared. Now we substitute with t equal 10, substitute with t equal 0, and take the difference to find this final answer. Also, definite integration based on its definition and based on describing it as the area under the curve have many interesting properties. Now, if the integration is from a up to a, clearly it will be 0, because in this case we have an area of 0. Now, if you change the limits of the integration, instead of integrating from a to b, you integrate from b to a. You have the same result but with a negative sign, because now we are moving in the opposite direction. And based on the fundamental theorem of calculus, instead of fb minus fa, it will be fa minus fb. So you have a change in the sign. Now if you have some function multiplied by constant k, you can bring this constant outside the integration. And this is very clear based on the fundamental theorem of calculus, or based on viewing this as an area under the graph scaled by constant k. And also you can distribute the definite integration over summation and over subtraction. And if you have an integration over some periods, so for example from a up to c, you can divide this interval into two parts, for example, because if you integrate the function from a up to c, this gives the area from a up to c under this graph. Now if you choose any point, say for example b, from a up to c, you can say that the total area is given by the summation of these two areas. Integration from a up to b to give the first area, the integration from b up to c to give the second area, and then you make summation. Now an very important note when you compute area, that if the graph is above the x-axis, you obtain a positive result. But if the graph is below the x-axis, you obtain a negative result when you apply integration, definite integration. Now, if you consider this function and make a different integration from this point, you compute this area. And you make integration from this point to this point, actually you compute this area, but you have a negative sign. The result will be negative a, not a. Because remember that how we calculate the area, we first start with rectangles. The height of each rectangle is the value of the function. In this case, the value of the function is negative, so the heights are negative, and then the total area will be the area in this case will be negative. So in general, if the function is greater than or equal 0, the graph is above the x-axis, the integration will be positive value. But if the function is below the x-axis, the graph is below the x-axis, the function is negative, then the integration will be negative. So now, what happens if you integrate from this point to this point? Actually, the result will be the sum of this area and this area with negative sign. So if you integrate from this point to this point, the result will be b plus minus a plus minus a. And this is what's called net area. It is the sum of the areas, but with sign taken into consideration. The area above the x-axis is positive, and the area below the x-axis is negative, and you add the areas with signs. What happens if you want to find the total area? You are interested in finding the area without sign. You want to find a plus b. So we have to split the integration into two integrals. Integration from this point to this point. Integration from this point to this point, and then add the result in absolute value. You have to add the result in absolute value. You have to get rid of the sign and then add the result. So we have two types of area. The net area is the area taking sign into consideration. So you can calculate it with a single integral. And you have also what's called total area. Total area is the actual area without the sign that appear in integration. And in this case, you have to define the integration into sub-integrals and then add them in absolute value. Let's consider an example. Assume that we have this function and want to find both the total area and the net area between this function and the x-axis from the interval from -1 up to 4. If you start with the total area, in order to find the total area, you have to find when this function is below the x-axis and when it is above the x-axis. In this case, in order to arrive at this conclusion, you have to find the intersection points of this function with the x-axis, which is the root. So we set this function equal 0, and we find 2 points. We have x equal 2 and x equal -3. So you have 2 intersection points, one of them at x equal -3 and the other at x equal 2. But now the problem is interested in the area from -1 up to 4. So we have to consider only the intersection points at 2. So the graph of this function from -1 up to 2 is, for example, above the x-axis, and then from 2 up to 4 is, for example, below the x-axis, or the opposite. It doesn't matter. So now if you want to find the total area, you have to integrate from -1 up to 2, and then from 2 up to 4, and then sum the result in absolute value, irrespective of the appearing sign. So to find the total area, we integrate first from -1 up to 2, and then from 2 up to 4, and you have to sum them, but in absolute value. This is the total area. For the net area, it is very simple. You integrate over the whole interval from -1 up to 4, single integral, and then get the result. In this case, will be a negative. It is clear that negative. Why it is negative? Because the area below the x-axis is greater than the area above the x-axis. The calculation of net area and total area is related also to displacement and distance, because if you calculate the net area, sum the areas taking sign into consideration, consider the area above the x-axis to be positive and the area below the x-axis to be negative, and then add the result. This is equivalent to calculating the displacement, assuming that you integrate the velocity function. If you integrate the velocity function as a single integral, within this integral, the velocity function in some interval are positive and in some other intervals are negative. In this case, you are calculating the displacement over the interval from A up to B. But now if you want to find the total travel distance, you have to divide the interval, and consider the parts when v of t is positive separately, and also the parts when v of t is negative separately, and integrate each of them and then add the result in absolute value. For example, if you are integrating this velocity function over the interval from a up to b, and it happens that the velocity function in this case is a positive function, and in this case it is a negative function. So from a up to c, the integration will be positive. It represents displacement in some specific direction, and the integration from c to b, it will be negative, representing displacement in the other direction. So if you make a single integral from a up to b, actually you are calculating the displacement, adding these two result, taking sign into consideration. This positive displacement and this negative displacement, you add both. So you calculate the displacement. But now if you want to find the total travel distance, here we have some distance, and here we have another travel distance irrespective of the sign. So in this case, if you want to find the total travel distance, you have to integrate from a up to c, and then integrate from c up to b, and then add the result irrespective of the sign, add the result in absolute value. Let's consider an example. We have a particle moving with this velocity function. We want to find both the displacement and distance over the interval from 1 up to b. Displacement, very simple. If you want to find displacement, you make a single integral from 1 up to 4. This is the displacement. Now, if you want to find the distance, you have to solve it as the total area. You have first to find the intersection points with the time axis, with the t-axis. You simply, if you consider the intersection point of this function, you will find that you have a single intersection point within this interval from 1 up to 4, which is 3. So we have to integrate from 1 up to 3, and then from 3 up to 4, and then add the result with absolute value. Actually, if you put this function equal 0, v of t, you have two roots, you have two solutions, t equal 3 and t equal -2. But actually -2 is outside our interval, and actually t is negative is not accepted because in our case t represent the time. So we have a single intersection point which is 3. So we have to divide the integration from up to 3, and then from 3 up to 4, and then add the result in absolute value. This is the first part about the definition of definite integral as a limit of a sum. Remember this very well. And also fundamental theorem of calculus, which relates the calculation of definite integral to indefinite integral. Now, the second part of the lecture consider some examples about evaluating a definite integral and some important notes. The first set of examples are based on calculating the area under the curve, which is given by a definite integral. But in this case, we consider some examples for which we can calculate this definite integral based on using some geometrical rule to evaluate the area. Instead of applying the fundamental theorem of calculus, we are going to solve this problem by considering the area represented by this integration and calculate this area with some geometrical rule. Let's consider this example. We want to evaluate this integration of modulus x minus 1 from x equal -2 up to 2. Now, this function modulus x minus 1 has this graph, and this simply can be viewed if you consider this function to be defined over two intervals. This function is x minus 1 when x minus 1 is greater than 0. So it is x minus 1 when x is greater than 1. And actually, it is negative x minus 1 when x is smaller than 1. So actually, this function represents two straight lines. When x is greater than 1, it is x minus 1, which is given by this line. You can draw this line simply by taking, for example, x equal 1, you get y equal 0, and if you put x equal 2, y will be equal to 1. So we have this straight line. Now for x smaller than 1, you have another straight line given by negative x minus 1, and you can simply draw this straight line. Now the integration of this function, which is given by these two straight lines, from negative 2 up to 2 is given by this area, and actually it is the area of two triangles. You can simply calculate the area of this triangle, half base times height, and also the area of this triangle. And so now the total area represent the value of this definite integral. So you can find the value of this definite integral by adding a1 and a2. Let's consider another example. In this case, we want to find the definite integral of this function, root 9 minus x squared from 0 up to 3. Actually, if you want to apply the fundamental theorem of calculus to solve this problem, you have to find the indefinite integration of this function. You have to find the antiderivative of this function. And actually, till now, we don't have a way to find the antiderivative of this function. Actually, solving this problem as an indefinite integration problem need what's called integration techniques. Specifically, it needs what's called trigonometric substitution, which will be considered inshallah in math 2. So we can solve this problem by applying a similar idea. Now this function y equal root minus x squared, 9 minus x squared, y equal root 9 minus x squared, represent the graph of this circle, actually the upper half of this circle, because if you make squaring of both sides, you get y squared equal 9 minus x squared, which can be written as x squared plus y squared equal 9. It is clear that this relation represents a circle whose center is the origin point and radius equal 3. But this positive square root means that we take the upper half of this circle only. So now this integration represents the area under this half circle from x equal 0, this origin, up to x equal 3. And clearly this area represents the quarter of the area of this circle. So this integration is given simply by 1 over 4 multiplied by area of this circle, which is given by pi times r square, which is 9. So we can simply solve this definite integration problem without using the fundamental theorem of calculus, without going into the problem of finding the antiderivative of this function, by considering this definite integral as an area problem and then use some geometrical rule, in this case the area of a circle, to evaluate this definite integral. Let's consider another idea, similar idea of this set of examples. Consider, for example, the evaluation of this definite integral. Again, evaluating this integral based on the fundamental theorem of calculus may be hard, because we are asked now to find the antiderivative of this function, and this somehow is hard. But as we did in the previous example, if we consider this function and make squaring, you finally arrive at this relation between x and y. And again, this relation represents a circle, but now this circle is shifted. The center is at 1 and 0, and radius equal 3. So this is the graph of this function. Now if you want to integrate from negative 2 up to 4, actually it is the area of this semicircle, and you can find it very simply. A similar problem if you consider the integration of this function. Again, this function, if you simplify this expression, you get finally this relation, and again this relation represents a shifted circle. The center is at 0 and 1, and radius equal 2. So now this is the graph of this semicircle. You want now to integrate this function from x equal negative 2 up to 2. You want to find the area below this graph, or between this graph and the x-axis, from x equal negative 2 up to x equal 2, this shaded area. And in this case, this shaded area represents the area of this semicircle, but we have also to add the area of this rectangle. So this definite integral will be given by the area of this semicircle plus the area of this rectangle. A final example can be given by this function. Now we want to find the net area and the total area between the graph of this function and the x-axis over the interval from 0 up to 4. What does the graph of this function represent? Now this part of the function can be simply written as x squared plus y squared equal 4. So it is a standard circle, a simple circle whose center is the origin point and radius equal to. And now you can consider also the graph of this function as we did in the previous example by saying that if we name this function to be y and make squaring, then we have y squared equal 1 minus x minus 3 all square. If you collect x and y in one side, you have x minus 3 all squared plus y squared equal 1. So it represents a circle shifted at 3 and 0 with radius 1. This is the center, 3 and 0, radius equal 1. Because you are taking the negative square root, so it is the lower part of the circle. It is lower semicircle. So this function defined on these parts represent the graph of this semicircle and the graph of this semicircle. Now if you want to integrate from 0 up to 4, from this point up to this point, you want to find the net area and the total area. To find the net area, simply you take the area of this quarter of the circle with positive sign and add it to the area of this semicircle, but this area will be a negative sign. So you calculate this area, but consider this to be a positive area and this to be a negative area, and then add the results. This to calculate the net area. To find the net area. This is the area of this quarter, and this is the area of this semicircle. But you consider this to be negative, and then add the result. If you want to find the total area, so you add the same two areas, but now consider both to be positive. So we add the area of this quarter of a circle to the area of this semicircle. This is the total area. Also, in this set of example, we consider what's called symmetry properties, and this is very important. It is related to integrating as a definite integral even and odd function. If the function is an even function, have a symmetry about the y-axis, and also there is a symmetry in the interval over which you are integrating this function. You integrate some even function from negative a up to a. This represents this area. Based on the symmetry of the function, the area to the left of the y-axis equals the area to the right of the y-axis. So you can consider only this area and multiply by 2. So the integration from negative a up to a is given by the integration from 0 up to a multiplied by 2. And if you want to solve this problem by simplifying it first to this side, this usually is much simpler than using this side, because if you substitute with 0, usually this will be simpler than substituting with negative a. Now if you consider the function to be odd and you want to integrate some odd function from negative a up to a, odd function has symmetry about the origin. If you integrate from negative a up to a, this area equals this area irrespective of the sign. But if you make integration from negative a to a, this area will be considered negative. So now if we add both areas, this with positive sign and this with negative sign, then the total area will be 0. So in general, if you integrate some odd function over a symmetric interval from negative a up to a, the result will be 0. A typical example for using this symmetry property is this example. We want to integrate this function over this interval. This interval is symmetric about the origin point, and this is the starting point. This is always the starting point in using these symmetric properties. We have an interval which is symmetric about the origin, integrating from negative a up to a in general. from negative 1 up to 1, from negative 2 up to, and so on. Now, if you have a look at this function is not even and also is not odd. But you can consider this function to be the sum of two functions. 1 over this denominator plus this function over the same denominator. Now, this function is clearly even because if you replace x with negative x, the result will be same. And this function is odd because if you replace x with negative x, then this sign x have an extra negative sign. So this function is an odd function. If you integrate an odd function over this symmetric interval, the result will be 0. So this part of the integration will be 0. And for the other part, this is an even function. Because this is an even function, you can replace it with double the integration from 0 up to 1. And now you can find the integration of this function using the fundamental theorem of calculus by finding first the antiderivative of this function, which will be tan inverse x. This will be tan inverse x. And then substitute with the limits to calculate the final answer. Tan inverse 1 will be pi over 4 and tan inverse 0 will be 0. So it is pi over 4 minus 0, which is pi over 4. So the main idea in this example is that we consider this integration and then we observe that the interval over which we are integrating is symmetric about the origin. So you have to take care of the symmetry properties. We find that we can break this function into two parts. One of them is an odd function, so the integration will be 0. And the other part is an even function, so we can consider it simply by integrating only from 0 up to 1 and then multiplying by 2. So we have to multiply here by 2. So this is multiplied by 2 and the final answer will be pi over 2. The last example is a technical note about the integration of this function. Actually, the integration, as we described in the indefinite integration problem, the integration of 1 over 1 minus x squared as an indefinite integration problem is given by what? Tangent inverse. It is tangent inverse x plus c. Actually, you can say also, and this is correct, the result is cotangent inverse. You usually use tangent inverse. But if you use cotangent inverse instead of tangent inverse, you are correct. You are correct. And you can verify this by calculating the derivative of cotangent inverse. The derivative of cotangent inverse. As we described when talking about the inverse hyperbolic function, we notice this important relation that cotangent inverse x equal tangent inverse 1 over x. Cotangent inverse x in general equal tangent inverse 1 over x. So if you want to find the derivative of cotangent inverse x, it will be the same as derivative of tangent inverse 1 over x. Now the derivative of tangent inverse is 1 over 1 minus the square of this term. But this term is not x, so applying the chain rule, you have to multiply by the derivative of this term, which is negative 1 over x. If you make a simplification, the result will be 1 over 1 minus x squared. It is exactly this function. So the derivative of tangent inverse is this relation, and also the derivative of cotangent inverse is also the same relation. So you can consider the solution of this indefinite integration problem to be tangent inverse or cotangent inverse. Both are correct as an indefinite integration problem. But now, what about definite integration? If this integration of this expression 1 over 1 minus x squared from a up to b over some definite period, for example, from negative half to half, or from, for example, 3 up to 10, can you apply tangent inverse or cotangent inverse? Can we say that both expression give the required result? The answer is not. Why? Because now tangent inverse and cotangent inverse has different domains. You can remember that the domain of tangent inverse is from negative 1 up to 1. The domain of this function is from negative 1 up to 1. So we can find tangent inverse only when x is a fraction. positive or negative. You can find tangent inverse half, tangent inverse 1/3, tangent inverse negative 1/4. You have to find, you can find tangent inverse only for x in this interval, fractions. But now, what about cotangent inverse? As we said, cotangent inverse x is tangent inverse 1 over x. So if you want to find cotangent inverse of some number, then the inverse of this number should be a fraction. So you can consider only cotangent inverse for 2, -2, 10, -5, and so on. But you cannot find cotangent inverse half, for example. So the domain of tangent inverse is from -1 up to 1, but the domain of cotangent inverse is the opposite domain. X should be greater than 1 or smaller than -1. So for tangent inverse, x is smaller than 1 in absolute value. Tangent inverse x in absolute value should be smaller than 1. But cotangent inverse, for cotangent inverse, modulus x, absolute x, should be greater than 1. So you choose between tangent inverse and the cotangent inverse based on the interval. If this interval is an interval that contain values within the interval from -1 up to 1, you have to apply tangent inverse. But if you are integrating for an interval that contain values that is greater than 1 absolute value, you have to apply cotangent inverse. Let's consider an example. But before considering this example, we write the result in general. Integration of 1 over, not 1 minus x squared, but in general, a square minus x square. We learned in indefinite integration problem this will be 1 over a tangent inverse x over a. And we now say that it is also equal to 1 over a cotangent inverse x over a. Both results are correct from an indefinite integration point of view. But now, for definite integration, you say that this result can be used when modulus x is smaller than a instead of 1. And this result will be used when modulus x is greater than a. Consider, for example, these two integrals. We want to integrate 1 over 1 minus x squared from 0 up to half. Now, this period from 0 up to half is within the interval from -1 up to 1. We integrate from 0 up to half over this interval. So we apply tangent inverse. We apply tangent inverse. But now the other integral is from 2 up to 3. From 2 up to 3. So in this case, we apply cotangent inverse. For the first integration, because this integration period is within the interval from -1 up to 1, so we apply tangent inverse. But for the other integral, the interval is outside the period from -1 up to 1, so we have to apply cotangent inverse. So the first integration is based on tangent inverse, but the second integration is based on cotangent inverse. Here we may have some question: what happens if we integrate, for example, from 0 up to 3? The starting point is within the interval from -1 up to 1, and the final point is some point which is greater than 1. Actually, this problem will be considered in math 2, inshallah, because at the point 1, the function is not continuous. The function tends to infinity. And this type of integration is called the improper integral. So such question is not a part of math 1, but will be considered, inshallah, in math 2. So that's all for definite integration. We consider the definition of definite integration as a limit of a sum, and represent the relation with indefinite integration based on what's called fundamental theorem of calculus, which represent the simplest way to evaluate the definite integration based on finding first the antiderivative, and you consider different example to apply the theorem, and consider also the definite integration to be an area. And this is the last lecture of this course. Thank you very much.